All right, so I guess this is going to be the new normal for maybe at least another month, maybe the rest of the semester, we'll see. But please let me know if you have any problems either hearing this PowerPoint or viewing any of this PowerPoint. Please just let me know. Also, if you have questions about anything that I'm doing, also please let me know. I'm going to be checking my email every day, so I should be able to respond to you within 24 hours. And just a reminder that this is a supplement to the PowerPoint that's posted online. I'm not going through that entire PowerPoint. I'm just really talking about a few things, but mainly doing math. Remember that I said the second part of this semester, it's very heavily math based. And so I'm going to try and work as many problems as we can in this. So last time we talked about speed and velocity. We talked about some types of motion, acceleration, balanced and unbalanced forces, and the bulk of what I'm going to be doing today is Newton's three laws. But there will also be some momentum, and we're also going to talk about mass versus weight first. So in everyday speech, we really use mass and weight interchangeably. But in terms of science, they do have very two specific definitions. So first, with mass, mass is going to be a measure of matter in an object. So remember, matter is anything that has mass and takes up space. So mass is just a measure of matter. Whereas weight is a measure of the amount of gravitational force. So its weight depends on gravity. In terms of what our unit of measurement is for these two, so for mass, our SI unit is going to be the kilogram, which is abbreviated kg, and weight's going to be measured in newtons, and newtons is a force, and our abbreviation is capital N for newtons. So mass we measure with a balance. So like we have a triple beam balance, or in the lab we use what we call semi-analytical balances. Whereas weight we measure with a scale, and that should be familiar to you because when you want to take your weight at home, you step on a scale. And depending on how much gravity is pulling you down, depends on how much you weigh. However, that's a little different with mass. So in terms of changing location, does mass and weight change with location? And by location, I don't mean do I weigh one thing in my house and another thing in someone else's house. That's not what I'm talking about with changing location. I'm talking about really changing planets. Because gravity on Earth is going to be the same no matter where you are on Earth. So our weight is not going to change as long as we're on Earth. However, if we went to someplace different, like maybe the moon or Pluto, our weight is going to change. So that would be a yes. Our weight is definitely going to change because gravity is different on Earth than it is on Pluto. However, our mass is going to stay the same. So it stays the same. Let's see, stays the same. And that's because the amount of matter we have is going to be consistent. So not unless you literally lost weight while you were traveling from one place to the other in space, how much you have is how much you have. All right, so next is Newton's three laws. And again, I just want to do a brief recap on what the PowerPoint has to say. Try to sum this up here for you real quick. So Newton's three laws are, of course, based off of Isaac Newton and the observations that he made back in the late 1600s. So these are things that we've known for quite some time. And with these things, they only talk about, they don't describe everything. So a lot of these laws don't apply when we talk in terms of chemistry. However, everyday stuff that we do consistency, these laws are going to describe that. So Newton's first law, it's what we call the law of inertia. Okay, so it just basically says an object in motion stays in motion, and an object at rest stays at rest unless acted upon by an unbalanced force. And an unbalanced force could be anything. It could be a push, it could be a pull, any type that's going to change the pattern. So if we think about it, if I throw a baseball, okay, an object in motion stays in motion. Well, if I throw a baseball in space, that's absolutely true. That baseball is going to keep going, and it's never really going to stop. However, that's not so true on Earth, though, right? If I throw a baseball, we know it's going to hit the ground. Well, the reason why it hits the ground is because of the pull of gravity. So in that case, the unbalanced force is the pull of gravity. So that's why things, at least on Earth, may not seem like they always follow this model, but they very much do, because if it wasn't for that unbalanced force of gravity, if we threw a ball on Earth, it would just keep going. However, an object at rest stays at rest. If I put my computer down on a table, it's going to stay there until something comes along and moves it. It's not going to spontaneously jump off the table. In terms of Newton's second law is what we call the law of force. Okay. And the law of force states that an unbalanced force equals the object's mass times the object's acceleration. Can y'all hear my cat meowing? Alright, so I really knew there was no way I was going to get through this video without some animal making sounds. Regardless, we're going to keep on moving. So, law of force, we really just, honestly, we just use the equation to describe this law, which is just the definition in equation form. Force equals mass times acceleration. And so we'll be solving problems with that in a bit. Last, we have Newton's third law, which we call the law of action-reaction. So this law just basically states for every action, there is an equal but opposite reaction force. Basically, and I think the example it gives in the PowerPoint slides is that if you kick a ball, that's going to be your force. The equal but opposite reaction force is that the ball moves. And all these laws, really, honestly, they all go together. And they're all our ways of describing things with force. All right, so let's go ahead and do some practicing with Newton's second law. And just so we remember the equation, I'll write it here up top. Force equals mass times acceleration. In terms of units, force needs to be in newtons, that's a capital N. Mass needs to be in kilograms, and acceleration is going to be meters per second squared. So based off of this, 1 Newton equals a kilogram times meter per second squared. So let's go ahead and jump right in here and solve some problems. What net force is needed to accelerate 1.6 times 10 to the third kilogram car forward 2 meters per second? So it's asking me for a force, it's giving me a mass, and an acceleration. So the mass is going to be 1.6 times 10 to the third kilograms, and our acceleration is going to be 2.0 meters per second squared. And of course, the one thing I always ask myself before I start plugging into the equation is, are all my units in the proper form to use the equation? And here the answer is going to be yes. So I don't have to do any unit converting, such as grams to kilograms, and things like that. So force equals mass times acceleration, where mass is 1.6 times 10 to the third kilograms. Acceleration is going to be 2.0 meters per second squared. And this is going to equal 0.1, oh, excuse me. Let me erase that right there. see if I can get the right number in my calculator here. So this should equal 3.2 times 10 to the third. And when we combine our units, this gives me kilograms per meter times second squared. Or we can just as easily write this 3.2 times 10 to the third newtons. So either one of these answers would be acceptable. Of course, you take a multiple choice test, so just make sure you pick the one with the appropriate units. Also, remember that these problems are the exact same one that's on the PowerPoint. So you can always refer back there if you want to look at them blank and try and practice them yourself. Or if you'd like to pause the video right now and do the next one, that's also something that you can do. You can also, if you feel like you've got this, you can fast forward the video. So that's the wonderful thing about videos. Do what you need to with it. So I'm going to go ahead and do the next problem. So a baseball accelerates downward at 9.8 meters per second squared. And of course, 9.8 meters per second squared, that's our gravity. So everything's really going to accelerate downward at that speed. If the gravitational force is the only force acting on the baseball and is 1.4 newtons, what is the baseball's mass in grams? So here we're given a force of 1.4 newtons. We're given an acceleration of 9.8 meters per second squared, and it's asking us what the mass of the baseball is. And in particular, it wants the mass in grams. So here I can use my force equals mass times acceleration equation. Now I need to rearrange and solve for mass. So the way that I'm going to do that is I'm going to divide both sides by acceleration. That way we can get mass on a side by itself. So mass equals force divided by acceleration. All of my units are in the proper form to use this equation. So I'm just going to say 1.4 newtons divided by 9.8 meters per second squared. And this is going to give me 0.14 kilograms. Now, make sure you remember what the problem is asking. This problem specifically asks, what is the mass in grams? Okay, so we have to make sure to finish converting this to grams. So we have 0.14 kilograms. I know for every 1 kilogram, there is 1,000 grams. So kilograms cancel. So this should equal, I believe, 1,400. Or excuse me, 140. It should be 140 grams. Okay, so 140 grams would be our answer in this case for the baseball. For number 3, a sailboat and its crew have a combined mass of 655 kilograms. If a net force of 895 newtons is pushing the sailboat forward, what is the sailboat's acceleration? So here it's giving me a force, 895 newtons. It's giving me a mass, 655 kilograms, and it's asking for an acceleration. So newtons and kilograms are my correct unit. So all I need to do is rearrange this formula. So similar how I did on the previous slide, I have to get acceleration by itself. Last time we got mass by itself. So to get acceleration by itself, I'm going to divide both sides by mass. Mass is, of course, going to cancel out on the right. That leaves us with just acceleration. So acceleration equals force divided by mass. Here we have a force of 895 newtons, and we have a mass of 655 kilograms. And so 895 divided by 655, that gives us 1.37 meters per second squared. So that's going to be the acceleration of our sailboat. Lastly, for problem number 4, the net forward force on the propeller of a 3,200 gram model airplane is 7 newtons. What is the acceleration of this airplane? So it's giving us a force of 7 newtons. It's giving us a mass of 3,200 grams, and it wants us to find the acceleration. So we know we're going to use force equals mass times acceleration. But here, we're not just yet ready to use this formula. We need to make sure all of our units are correct. And for mass, they're not correct. So we need to make sure that we convert those grams into kilograms so we can use this formula. So I have 3,200 grams. I know that there's 1,000 grams in 1 kilogram. So 3,200 divided by 1,000 is going to give us 3, oops, I don't know why. Oh, what is this doing? Oh, there we go. Equals 3.2 kilograms. So instead of using this 3,200 number, we need to use 3.2 kilograms. All right, so now we have everything okay. We can go ahead and use the formula that we derived from up top, where acceleration equals force divided by mass. Our force is 7 newtons. Our mass in kilograms is 3.2 kilograms. So 7 divided by 3.2, that's going to give us 2.2 meters per second squared. The next thing that I would like to talk about is momentum. And again, I'm just recapping here and getting into some problems. So momentum is, or I should say, an object's momentum. So an object's momentum is going to be the product of the object's mass times its velocity. So the example that it gave you in the PowerPoint was, I believe, a truck versus the car. If they were going the same speed, which would have the same momentum. And then they also gave you an example of 2 cars. If one was going a different speed, but they were both the same mass, which would have the greater momentum. So in terms of that, we can, of course, always put this in a formula. So momentum equals the mass times velocity, which again is just our definition. Now, we start to run out of letters here in our alphabet. We don't want to have momentum as M because we already said that M stands for mass. So here we abbreviate momentum with a P. So keep that in mind, that momentum is abbreviated with a P here. In terms of units, for this formula, mass is also going to be in kilograms, and velocity needs to be in meters per second. So by force, that would make our units for momentum kilogram times meter per second. Do not get this confused with newtons, okay? Remember, a newton equals a kilogram times meters per second squared. Momentum, the seconds on the bottom, is not squared. Okay, so that's going to be a main difference here. So make sure you know what you're solving for when you do these things. So calculating momentum. Again, I'm just going to write our little equation up here as a reminder. Okay? And I'll go ahead and put that mass needs to be kilograms and velocity, just for us to remember now, is meters per second. So a 75 kilogram skater moves forward at 16 meters per second. What is the skater's momentum? So it's asking us to solve for momentum. It's giving us a mass of 75 kilograms. And we have a velocity of 16 meters per second. So everything's in the correct unit, so we're just going to go ahead and plug this into our formula. So momentum equals mass times velocity. So that's going to be 75 kilograms times 16 meters per second squared. This is going to give us a momentum value of 1,200 kilogram times meter second. So this would be our answer in terms of this roller skater's momentum. Next, this is asking us to calculate the velocity. So what is the velocity of a 135 kilogram ostrich running north with a momentum of 2,190 kilograms meters per second north? So here it's giving us a momentum of 2,190 kilograms times meters per second. And it's giving us a mass of 135 kilograms and is asking us to solve for the velocity. again, now's a good time for you to pause the video. Try and do this on your own. Make sure you're getting it. So with this, again, I look at it, everything's in the correct unit. So I know I can go ahead and use my formula. I do need to get velocity on a side by itself. In order to do that, I'm going to divide both sides by m, or divide both sides by mass. They're going to cancel out on the right, and this is going to leave us with velocity equals momentum divided by mass. So my momentum is 2,190 kilograms times meter per second, divided by 135 kilograms. Here you can easily see that kilograms cancels out. This is going to leave us with 16.2, and the only units we have left are meters per second. So this ostrich is able to run 16.2 meters per second. In terms of momentum, we have this idea of the law of conservation of momentum. So if we take two objects and there's a collision between them, momentum is going to be conserved. And that's because momentum is going to be transferred from one object to the next. So in terms of this Newton's cradle here, that's what we call this, and you may be familiar with it. So, and I hope the animation is working too. But if not, Google Newton's cradle and watch a video. So when one ball hits the other balls, it kind of triggers a chain reaction with you, if you will. What it's actually doing is transferring energy between all the balls, but we don't learn about energy until the next chapter. So in terms of this, in the law of conservation of momentum, what we start with momentum-wise is what we have to end with. So momentum at the start, and remember P equals momentum, has to be the momentum at the end. All right, and momentum equals mass times velocity. So this first ball, or what I'm going to call the first ball over here, it has some momentum. Okay, we can say it has a momentum of 2. This ending ball over here, this ending ball, once it's moved, it also has a momentum of 2. Everything is going to be conserved. Now technically, or I guess we should say in reality, okay, some of this transfer is actually going to be lost, okay? However, and it's going to be lost due to friction, okay? We'll talk way more about that in the energy chapter. Technically, the ending result wouldn't be 2. It would actually be a little bit less than 2. However, for the purpose of this and to make our calculations so much easier, we're going to consider that this is 1000% conserved, or I should say 100% conserved, and that nothing is being lost. So we're assuming that no energy is being lost. And even if we do have it being lost to friction, the amount that is lost to friction, if we add that to the ending momentum, it still equals what we have in the beginning. So again, regardless of whether we account for friction or not, it's still completely conserved. But again, in our problems, we're just going to take the easy way out and say what we start with is 100% of what we end with. So what does this mean in terms of calculations? So let's do our first example here. So calculating momentum. So we're going to play pool, and you know, I always have to explain to my high school students, pool means, you know, like the billiard balls. We're not actually going to play in a pool. Not all of them are familiar with the game of pool. So regardless, you hit a 0.23 gram cue ball, and it's going to move with the velocity of 0.8 meters per second north. It then collides straight on with the 8 ball, and of course, we're at the end of the game, so we're trying to go for the win here. When they collide together, the cue ball completely stops, and it wants to know what the momentum of the 8 ball is now. So guys, with these, I always like to draw pictures. They make things so much easier. So we're starting out here with our cue ball. Okay, and I've hit, I should make that actually say cue. All right, and we of course have our pool stick here, and we hit the cue ball with our pool stick, and it's going to forward move. Okay, so our cue ball we know is 0.23 kilograms, and we know the velocity of it is 0.8 meters per second squared. Now over here we have our 8 ball. Okay, currently our 8 ball is stopped at 0 meters per second squared. Okay, this cue ball is going to collide and hit the 8 ball. So here's like our starting picture. Let me draw. This is our start picture. Okay. And then in terms of our ending picture, our cue ball is stopped. Okay, so if it's stopped, it has no velocity. That's 0 meters per second. However, the weights, or excuse me, the mass is not going to change. However, our 8 ball's on the move now. Okay, so now our 8 ball's on the move. So it has some velocity that we have to try and find. And we're also going to assume that this mass is also the same. And this is going to be our end picture, our final picture, what happened after the event. So we have some event that happened at the start, and we have what happened at the end. So based on the previous slide, we know momentum's conserved. Momentum at the start has to equal momentum at the end. And that's what this little sentence is saying right here. Assume all kinetic energy of the system is conserved. So again, we're just assuming that nothing is lost to friction. So here it wants to know what the momentum is at the end. That's what this question is asking us. What is the momentum of that 8 ball? Well, if we know the momentum of the cue ball, that is the momentum of the 8 ball. So here, if we know the momentum of the cue ball, okay, we have the mass, which is 0.23. Let me rewrite that. Okay. So we know the mass, 0.23 kilograms, and we know the velocity, 0.8 meters per second. Those are the correct units that we need to use. So if we just plug it into the equation, we'll get the momentum of the cue ball. So 0.23 kilograms times 0.8 meters per second. So that's going to come out to, if we multiply those two together, we're going to get the momentum of the cue ball to be 0.184 kilograms times meters per second. Okay. So if that's the momentum at the start, that also has to be the momentum at the end, which is completely transferred to our 8 ball. So the last problem we just worked in terms of conservation of momentum problems, that was a little easy. We just had to say that the momentum at the start equals the momentum at the end. Not a problem. And of course, this is where momentum equals mass times velocity. These next two are going to be a little bit more challenging. Again, go ahead and stop the video now if you want to and try and figure this out. But definitely after this problem, make sure you stop the video and try and figure out the next one on your own. So here we have a friend that throws a 12 kilogram medicine ball at you with a velocity of 1.8 meters per second north. You are standing still with roller skates on, and you have a mass of 65 kilograms. You catch the ball and roll backwards. This is asking what is our velocity after the collision. So again, I'm going to draw pictures here because I really feel that it makes it easier to kind of visualize and organize information when we do this. So you have a friend, okay, and your friend's holding a medicine ball. This medicine ball is going to be 12 kilograms. Your friend throws this medicine ball at you with a velocity of 1.8 meters per second. Okay, here you are standing right here. Okay. And it says you're standing still with roller skates on. So I'm going to draw some little skates here. Okay. And this is our starting event, or our beginning event. Okay. Now, the ending event is going to be once you catch it. So over here, when you're at the start, you're standing still. If you're standing still, you have a velocity of 0 meters per second. Okay, and you still have a mass. Your mass is going to be 65 kilograms. After the event, you catch the ball. So it says up here, you catch the ball. So now we just have you. Okay, you still got your roller skates on. Okay, and now you've caught the ball. Okay. It says, what is your velocity after the collision? Well, you're definitely moving now. Okay, so we have to try and figure out what velocity you have. in terms of information we still know about this ending picture. Okay, so what's on the end? Okay, we know that the mass of the medicine ball is 12 kilograms. We know that your mass is 65 kilograms. That's currently all the information that we know. We have to try and find a way to figure out what is your ending velocity. Well, in terms of velocity, okay, we know velocity and momentum are related through the P equals m times v equation. So in order to solve this equation, we need to know two things. We need to know the momentum and we need to know the mass. We got the mass down, that's not a problem. So in order to solve this, we need to know the momentum. Well, you can figure out the momentum at the end if you know the momentum at the start. So let's figure out the momentum at the start. So the momentum at the start equals your mass times velocity, okay? So in terms of, you have two masses and two velocities here, okay? So we have the mass and the velocity of the ball, and we have the mass and the velocity of you. Now, your velocity is 0, so anything times 0 is going to be, well, 0. So we can erase this part. So in terms of the only thing that really has momentum here, the only thing that's moving is this medicine ball. So we're just going to use those numbers to do this calculation. So momentum is mass, which is 12 kilograms, times the velocity, which is 1.8 meters per second. So here, 12 times 1.8 is going to equal 21.6, and our units are going to be kilograms times meters per second. So this is our starting momentum. Based off the law of conservation of momentum and the fact that we say everything is conserved, this is also going to be your ending momentum. So here your ending momentum is also 21.6 kilogram times meters per second. The other thing we need to know over here is mass. And you also have to remember it's going to be total mass. Okay? So total mass is you have a 12 kilogram medicine ball plus you, which is 65 kilograms. So 12 kilograms plus 65, what is that, 77? Right? So you have a total mass of 77 kilograms. So we need to make sure we put all of that mass into the equation. And now we can finally solve for final velocity. So if we rearrange this equation, velocity equals momentum divided by mass. Momentum is going to be 21.6 kilograms times meter per second divided by 77 kilograms. Kilograms cancels out, leaves us with meters per second. So here our ending velocity is going to be 0.28 meters per second. And again, if I lost you somewhere, of course, you can always send me an email if you feel like I did some funny math. Send me an email, ask me a question. Also, just replay this problem. Stop it, go figure out, try and work it by yourself. Come back, see how the explanation was, and watch it again. So definitely make sure you're taking advantage while you're doing that. All right, so our last calculating momentum example, and this is going to be like the one we just did with the medicine ball and the person on the skater. So I highly encourage you to pause this video right now and try and work it out on your own. So here we have a 22 kilogram child running at 2.4 meters per second east. They jump onto a 12 kilogram sled, which was initially at rest. What will the velocity of the child on the sled be immediately after the child jumps on the sled? So let's draw our start picture. Okay, so our start picture, we have a 22 kilogram child. Okay, and this child is running at 2.4 meters per second. And we have a sled, which I'm just going to draw like that. The sled is 12 kilograms, and it's 0 meters per second. That's our starting image. Our ending image, or I guess I should say the ending result, is that the child is now on the sled. Okay? What we still know is true is that this child is 22 kilograms and the sled is 12 kilograms. None of that has changed. However, here we're trying to calculate what is the velocity of this sled right after the child jumps on it. So to really solve this problem, okay, we're going to use momentum equals mass times velocity. So again, we know the mass here. Okay, the mass is going to be 22 plus 12 kilograms, which should be 34 kilograms. That's our total mass on this side. However, in order to solve this, we must know momentum. Okay, if we're trying to find velocity, we must know this momentum. So we need to calculate it. And since we're not given velocity, we're going to have to look somewhere else. And where we're going to look is the start, because if we can figure out the momentum of the start, we can plug that in for the momentum of the end, because of course it says that all energy of the system is going to be conserved. So for this, the momentum of the start, okay, momentum equals mass times velocity. Again, we're not taking this sled into consideration because its velocity is 0 meters per second. So that would just be 12 times 0, which is going to be 0. So we don't have to take that into consideration for the starting momentum. We just have to take into consideration the mass of the child, which is 22 kilograms, and the child's velocity, which is 2.4 meters per second squared. So this is going to give you a total momentum of 52.8 kilograms times meters per second. So if that's our starting momentum, that also has to be our ending momentum. Kilograms times meters per second. So now we have all the information that we need to solve this problem. So velocity is going to equal momentum divided by mass. Okay. Our momentum is 52.8 divided by 34. Let me go ahead and write my units out here to keep with consistency. Divided by 34 kilograms. So here, my velocity is going to equal 0. Excuse me, it's not 0. That should be 1.55 meters per second. Right? And now technically, of course, in this video, we've been talking about velocity. And one of the things that we talked about last time, the difference between speed and velocity is that velocity has a direction. So if you want to be formal on this, it would be 1.55 meters per second. Does it give us a way the child goes? East. So in the problem, it told us east. So the velocity would be 1.55 meters per second east. So that's going to, I believe, wrap up the video for today. So again, if you have any questions, please email me. Make sure you're staying up to date with notifications on Canvas, and hopefully this will all work out for us.